This is a demonstration of the autofocus mechanism on the Huawei P40 cell phone. This video is from AndroidAuthority.com, which has an article reviewing dual pixel autofocus. Dual pixel autofocus is a version of phase detection autofocus. In phase detection autofocus, you observe a scene with different parts of the aperture blocked off. If the scene is exactly in focus, then the sub-images from each part of the aperture will overlap, as shown here. But if it's defocused in either direction, then you'll get a relative shift in the images from each of the sub-apertures. And so by measuring that shift, you can determine the amount of focus. And without having to scan to maximize contrast, you could find the appropriate focus immediately. So as I said, this is used in a lot of modern cell phones. Here's a website where Samsung talks about its strategy. Traditional phase detection autofocus, which is not very traditional, it's just a few years old, but people had built these phase detection pixels into cell phones, and so that you have the RGB color filter array, but then you also have pixels that are specifically designed to measure the quality of the focus. And in a conventional mobile device, those were about maybe 2 to 3% of all the pixels would be phase detection autofocus pixels. As I said, the modern strategy is to use this dual pixel autofocus. So Samsung is proud of their dual pixels, where under each lenslet for each color filter, they have 2 pixels, and they can do phase detection analysis to consider the focus by looking at the relative intensity on those 2 pixels. And now they've even got pixels that are oriented in various directions, with the diagonals for the green pixels and the straight lines for the red pixels and the blue pixels. So this is the reason why when we look at cell phone specifications now, you see in this Galaxy S25, they're using 50 megapixel sensors, even up to 200 megapixel sensors, and this is oversampling. The pixel size is much smaller than lambda f number, so it doesn't make sense to sample at that rate from the perspective of Nyquist sampling of the actual optical image. But if you consider that you're using the pixel in split form to consider the focus quality and to measure color, then it may make sense to have these kind of oversampled pixels. Today, our focus is on focus strategy, and we want to talk not really about phase detection or dual pixel autofocus, because in the modern world, I don't think it's a good idea. Let's talk about a better approach. Computational imaging. Episode 68, Focus Sampling. We discussed focus several times in these episodes. Most recently in episode 50, we talked about focus in incoherent imaging systems and talked about the depth of field under various focal assumptions. A fundamental concept in considering focus is this hyperfocal distance, which is the focal point at which the point at infinity is at the maximal acceptable defocus, and then the near point when we focus at the hyperfocal distance is the hyperfocal distance over 2. The hyperfocal distance is also proportional to the maximal defocus parameters and the maximal defocus aberration that we can have in an imaging system. So given that, if we want to focus at some specific range, Z0, we can express Z0 as a fraction of the hyperfocal distance, and then our depth of field follows this form of the ratio of the Z0 to the hyperfocal distance defines our focal range. And in particular, for example, if alpha here was 1, then our near point would be hyperfocal distance over 2. If alpha was 3, then our near point would be the hyperfocal distance over 4, and our far point would be the hyperfocal distance over 2, and so on. So given that, for any specific range Z0, we can define a depth of field as shown here, which basically comes out to be the range squared divided by the hyperfocal distance. The hyperfocal distance grows with the square of the focal length. So here we see plots of the hyperfocal distance as a function of focal length for different f numbers, f2 and f10. So if we go to like a 25 millimeter focal length shown here, we expect our hyperfocal distance is going to end up being a couple or 100 meters or just over 100 meters. Here we've assumed that the circle of confusion is proportional to lambda f number, and so that's how we've determined the hyperfocal distance. And if we do that, the hyperfocal distance is the focal length squared divided by the f number squared, where the f is in millimeters. If we increase the F number, the hyperfocal distance gets shorter, shown at the bottom plot. So, if we have a 25 millimeter focal length and we then would focus at the hyperfocal distance, we would have in focus image, let's say down to like 50 meters. So our near point would be 50 meters. We want to focus closer than that. Then we have to adjust the focus, but the hyperfocal distance also allows us to analyze the depth of field at any range. The number of focal states we need to image from some near point, z sub near, to some far point, z sub far, is given by this relationship, where we know that the depth of field we have at any range is h divided by alpha minus 1 to zh divided by alpha plus 1, where alpha is the ratio between our range to the hyperfocal distance. Okay, so this is the number of focal states we need, and if we have a short focal length lens where the hyperfocal distance is 2 meters, then we don't need any focus adjustment. We can go from 2 meters to infinity. But if we determine that we want some resolution on a target where we don't have infinite depth of field, then we have to develop an adaptive focus system to cover the range. So our depth of field again has this form. We determine the hyperfocal distance and the range. Typically the hyperfocal distance is going to be much larger than the range, so this would go away, and so this is going to be approximately z naught squared over the hyperfocal distance. But typically we don't say here's a focal length and what's our depth of field. Most typically in imaging applications we say this is the resolution we want on target. So we say, for example, we want a ground sample distance delta on the target, and then the focal length is determined by the ground sample distance, or the focal length that we use is determined by what focal length do we need to get the ground sample distance at the range that we want to work at. So that means that the focal length is proportional to the ground sample distance. We plug that in, and it turns out that the depth of field given a ground sample distance is not a function of the focal length or the range at all. It's just a function of what's the ground sample distance we're trying to get. Now, so if that depth of field is much less than the hyperfocal distance, we're going to have to use some number of focal states to image over the full range. So we have to do some kind of adaptive focus. So for example, in cell phones, you might want to focus to read text. You'd focus at 10 centimeters, and then you want to focus to objects out to some range. So to cover that range, a cell phone needs an adaptive focus mechanism, and that's why they put these dual pixel phase detection autofocus mechanisms into cell phones. Now, this is all based on the idea that the strategies we have for controlling autofocus are we can do image-based focus, where we look at the contrast in the image and search for a focal state that maximizes the contrast. We can do phase detection, where we've got a measurement that's proportional to the defocus, or we could do some active ranging system with, for example, a LiDAR or a acoustic wave ranging system. In my opinion, none of those are currently necessary, because it turns out you can look at an image and determine how much out of focus it is. And whatever if you could look at an image and say that's way out of focus, here's how much I want to adjust, a computer can probably do that too. So we worked on this paper, which is in Transactions on Computational Imaging, where we use deep learning to control the autofocus. And so in this system, you have a discriminator that looks at the image and determines not just that it's defocused, but how much out of focus it is. And so rather than having to use phase detection hardware, modern systems can just look at the image for a well-focused image and detect how far you need to adjust to move it into focus. And so in this paper, the network was trained for images at various levels of defocus, and then this was the predicted amount of defocus. And the network did a very good job at estimating that. I really want to say that I do believe that over time, more sophisticated pixels are needed. And in a couple lectures, we're going to talk about pixels that measure interferometric measures of the field. But I don't believe that pixels that are specifically designed to measure defocus are actually a good idea. There's a Jupyter notebook on the GitHub site that analyzes neural focus control, and here's examples from that. So we have images taken, in this case, from the CFAR database that then we've applied some defocus to. So each of this frog is this frog with a very small defocus, and we randomly selected some defocus value to apply to those images, and then we train a network to estimate what is the defocus parameter, and the network does very well. So this is the predicted defocus versus the true defocus for these images. So this idea of just looking at an image with a standard sensor as opposed to making a special dual pixel sensor suggests that the dual pixel is not necessary. This is a big deal, of course, because if you're actually going to take you're going to make a 10 megapixel image, but you're using 50 megapixels to measure it, you're probably sensing way too much data and maybe have too much noise in your data. So the design of these things, this is the point of this course, of course, is we should compare different physical sampling strategies and algorithms to figure out the optimal design. And we're probably not there in terms of what's actually being done with focal planes, but as we saw with the temporal sampling in the previous episodes, focal planes have a long way to go to get to optimal design, but to make any optimally designed focal plane is a very expensive prospect, but hopefully we're making progress in that regard. One of the key problems we have with focus control, of course, is that it's an ill-defined problem, as commonly stated. There isn't an optimal focus for a camera. The world is three-dimensional. So we don't want to adjust the camera and say we've captured all the world. We want to find a think of the focus system as a control system that tries to recover the image, and this is where neural processing is increasingly central to the way we think about focus. So the same paper that I referenced from Transactions on Computational Imaging expands on this topic to consider a system where there's a agent that from a given state of the image, a given state of the system, estimates what the next best focus is. And so the agent is given the current measurement, which might look like this, and then the estimated all-in-focus image in this case, and then from those chooses a next measurement and then generates a next estimate of the all-in-focus image. So here in the measurement system, the foreground is out of focus, the background is in focus. The current agent has the midfield and the background out of focus. After we make an additional measurement and combine those, then we get a better all-in-focus image. And so this system goes through sequences that look like this. The bottom row is where the agent chooses to focus, and the paper discusses a couple of different strategies for controlling the agent using either reinforcement learning or a rule-based algorithm. You see here, this is the current measurement, and this is the current estimate of the field, and here the agent has decided this part of the image is too much out of focus, and so in the next step you measure there, and so that this is in focus, and then you get an estimate of that being in focus, and now this foreground is too much out of focus, so the next measurement measures the foreground, and then you get an estimate of the scene where more and more of the scene is in focus, and then and here again are the results I showed at the end of episode 67, where we show at the upper left the current focal region. The center is the current image being measured, and at the lower right, the current estimate of the all-in-focus image. Now, of course, here we see that the world is actually four-dimensional. We have 3 dimensions of space and time, and so the focus mechanism for the future computational imaging systems is not how do I find the best focus for the current scene. It's how do I track the focus to control, to estimate the scene when both the scene is moving and I want to get the full 3-dimensional version of the world. Okay, so this is the future of focus is that you have this kind of dynamic agent that's going to control focus. But of course, we're talking about how we should sample focus, and in the last several episodes, we're interested in how we should sample spectra and how we should sample time. And we've seen that array cameras are a powerful tool in this regard. And so there's this paper that we've talked about in the previous episode about physics-aware transformers to stitch images from multiple cameras, and certainly we would use that for spectra and time and field of view and focus. So in this particular example from the paper, we capture 4 different color channels and then combine that to create a in-focus color image where this is the estimated scene, this is the measurement with a low resolution RGB camera, the resolution estimate with the measurement with a high resolution monochrome camera, and this is the combined data from the transformer network to integrate the scene. We can do this same kind of multi-frame sampling, of course, with multifocal cameras, so we can have different ranges rather than doing a set of focal states to measure over range in time. If we want to do that in snapshot form, we can have a camera that measures the far range, a camera that measures the near range, or the mid range, and a camera that measures the near range, and combine them together. So this is work that Minghao Hu did in our camera lab at the University of Arizona using the physics-aware transformer to combine data from these 3 different cameras with different focal lengths and different field of view: a 5mm, 12mm, and 25mm camera. Each of the cameras is set to be in focus over some depth of field, so the 25mm covers a range, from about 11 meters to 17 meters. The 11mm covers this mid-range, and the short focal length is in focus at all ranges, of course, but it doesn't have the ground sample distance we want at the far range, and so we only use the data for that in the range from 1 to 5 meters. So in this particular case, to increase the sensitivity, the long focal length cameras, those were monochrome, and then we use color in the short focal length camera. And then you get data for objects at different distances with different ranges or different qualities. So objects that are nearby are out of focus for the 25mm lens, but as we go to further ranges, those are in focus. The 12mm lens has objects in focus in the mid range, and the short focal length lens, these objects are in focus at this range, but it doesn't have the resolution at that range because of the short focal length, but it does have the ground sample distance we want at 3mm. And so then we can fuse the color and the monochrome using the physics-aware transformer. And so these are example images at 7mm range. The 7-meter range of the fused image with the 12mm, and the 5mm produces a high-quality color image. And then if we did this range, the 25mm is not in focus. But if we go to a 13mm range, the 25mm range is in focus. So these system can choose the camera array that we want to create a well-focused image. And of course, these are trade-offs that we have in designing these systems, is that we can change the focus dynamically over time, and we can use camera arrays to sample the focal state in an intelligent way. And then we don't think of the world as trying to just present the image that we've captured. We, of course, want to create a synthesized image from our data. As a simple example, there's also a Jupyter notebook on the GitHub site that does conventional image stitching. The example I showed just a second ago was this physics-aware transformer-based image fusion, but the example on the GitHub site takes a look at, here we have 3 images focused on the midfield here, the rear and the foreground are in focus in the different images. Conventional strategies for doing focal stacking with these images is very similar to panoramic stitching. We do key point matching, which of course is a little bit of a challenge because the focus is different in the different images, but works reasonably. After we find the key points, we can implement homography to match the images in pair. So this is the foreground focused image and the background focused image, and then this is the difference between the images after the homography is applied. And you see a substantial difference because of the difference in focus, but the basic homography is mapped to the foreground focused image onto the viewpoint of the background focused image. And then we can look at the images after the homographies have been applied. This is using a Laplacian operator on the images to find where the edges are in the different images. So the foreground is sharp on the ball, the background is sharp on the book, the midfield is sharp on this pencil holder. And so we can then use a mask based on where the Gaussian, where the gradient is highest, or where the Laplacian is highest on the different images, to choose which region we want to use from different images, and then we combine them together to get an all-in-focus image. So here's the 3 measured data images again, and then the all-in-focus image where the 3 are blended together to create an all-in-focus image. So the point of this again is that we want not to get a camera that measures an all-in-focus or measures a particular focus of the scene. We want to create systems that capture the optical data cube, so we can use arrays in time to get the all-in-focus data and then estimate the scene from that. So we've been through how do we measure spectra, how do we measure time, how do we manage dynamic range, how do we manage focus. These are all core sampling issues in digital imager design, and as we've talked about in this episode, we would like to use array cameras as one of the tools that we can use to capture the optical data cube. Next time, we're going to talk about why that is in somewhat more detail, where we're going to talk about lens design. This is an image of the Aware 2 gigapixel camera that used 200 micro cameras. Building this was a time-consuming effort. Here we see our lab at Duke University, where this camera was built, and Dave Kittle and Steve Feller and other members of our group working on assembling these things. That dome with all the holes in it, that's the mount point for micro cameras. Each one of the micro cameras is a 14 megapixel sensor. So by putting a couple hundred of those in there, we can build a 2 gigapixel camera. Here we tested, and then we went back in the lab and put the dome into this metal frame that you see in the background there, and then mounted all kinds of FPGAs and cooling elements to allow us to read out the data from this thing, and got it all assembled and went out and tested it. We want to talk about how we arrived at this design and why these kind of parallel array camera designs are an essential piece of building powerful cameras. And the end image here, of course, is the image that we published in Nature, showing a gigapixel scale image of a bird sanctuary taken with this camera. So we have tools to capture a lot of data, to capture the optical data cube. And we're finally going to arrive in our next lecture at a discussion of how the lens design comes about.